Hi, I am Pieter Abbeel, and I'm excited to be here to share with you what I think is the awakening of AI robotics that's starting right now. Before doing so, let me say a little bit about myself. I did my PhD at Stanford working with Andrew Ng. From there, I became professor at Berkeley, where I've been since 2008. I do research on AI and robotics. I'm the director of the Robot Learning Lab. I co-direct the Berkeley AI Research Lab. I do teaching, also in AI and robotics, and I do various other things. Often with the lab, we host kids to get them excited about STEM. So if you, in more normal times, want to bring some kids by, get them excited about science, math, and so forth, we're happy to host them. We often host technical deep learning tutorials as well as sessions for executives, which of course look at AI at the strategic level. And in fact, I also was an actor in a Verizon TV commercial where I was the robotics expert explaining the importance of 5G for the future of robotics. In addition to my role as professor at Berkeley, I do quite a few other things. I started a company called GradeScope, where we build AI to help teachers and professors with grading homework, exams, projects. This is now used at over 500 schools, and in fact, the company's been acquired by a big education company, Turnitin. For about 2 years, I was a research scientist at OpenAI, AI research organization based in San Francisco, initially largely funded by Elon Musk. And in 2017, I founded a new company, Covariant, and I'll say more about it later, but in brief, at Covariant, we build AI for robotic automation of manufacturing, warehousing, e-commerce, logistics, and so forth. And I'm advisor to quite a few AI startups. All right, enough about me. How about robotics? A lot of us are probably familiar with the current state of robotic automation, which I'll call traditional robotic automation. If you go to a car factory, what you see is something like this. Lots of robots, and these robots are super effective, super precise, tireless, doing whatever they are tasked to do. Amazing. But if you look under the hood, you realize that these robots are essentially doing repeated motion over and over and over. So you can only use this kind of traditional robotic automation if it's enough to just go through the same motions over and over. That's great for car manufacturing. Some other manufacturing electronics can benefit from it sometimes. But most of the things we do in the world, let's say with our hands, just repeated motion is not going to cut it. We need something that can see, adapt to what it sees, learn from its experience, become better over time, and so forth. So, when are we going to see those kind of robots? Well, many people have asked that kind of question. In fact, there have been movies made about this question. Terminator suggests that these robots are going to come from the future. I don't think they'll come from the future, the AI robots that we'll see. In Westworld, it's suggested that they will be among us and we won't even realize it. And then Rosie the robot is a helpful robot. So some scary scenarios, some helpful scenarios. But technologically, let's think about what is going to be the entry point for robots into our world. AI robots, robots that think, that do more than repeated motion. What do you think? When is it going to happen and how? I'll give you a moment to think about this. Well, I'll give you my answer. I believe this here is the quiet, under the radar entry point of AI robotics into real world value creation. Autonomous order picking. This was not possible even just a couple years ago. But what we see here is a robot autonomously fulfilling orders as documented by the New York Times, January 2020. It's a Knapp Piketty powered by Covariant brain. When you're looking at this, you might say, well, why is Pieter calling this the entry point of AI robotics? Well, let's think again about what does it mean to be an AI robotic system? What it means is to be a system that can see and adapt to what it sees, as opposed to traditional repeated motion automation. This robot is doing exactly that. It's operating in a warehouse that has 60,000 different SKUs, different types of items it's distributing. And these SKUs are rotating all the time. So this robot has not seen all these SKUs before. This robot is continuously seeing things it's never seen before, in configurations it's never seen before, and has to adapt its motion, where it's going to pick, how it's going to place, to whatever is in front of it. That's the kind of intelligence that's fundamentally different from traditional repeated motion robotic automation. And this here is the first documented instance of really seeing that in action. In fact, with this article came a 1 hour plus uncut video showing the robot adapting to every situation at hour, and in fact, to everything it encountered that day under scrutiny of a reporter. So, this is already happening, and it's ever becoming more important. And as this robot is doing this, it's learning. It's learning from its own experience here. It's becoming better over time. And from there, it'll be able to expand to new situations, possibly situations beyond this particular warehouse. In fact, it already has. Okay, so if you remember one thing from this talk, I would say it's this. AI robotics has just started to enter our world, and the way it's entered it is through order fulfillment in warehouses. Not some place where you'd see it. It's not like a Westworld amusement park or a Terminator come and take over the world, but it's quietly doing its work in warehouses, doing things that go far beyond repeated motion automation. All right, now let's try to start understanding this trend. Where is this coming from? What are the breakthroughs that this required, and where is this going? Well, as a starting point, think about AI robotics. The robot needs to see, and then to adapt to what it sees. So, seeing, you see a picture here, coffee mug, right? Well, how to write a computer program to know that this is a coffee mug? Not so easy, because the computer only sees numbers. And in fact, for decades, the computer vision community was trying to get a computer to understand what's in an image, and did not succeed. But this changed. In 2012, out of Jeff Hinton's lab at the University of Toronto, it was shown that we can now, with reasonable reliability, start detecting what's in images. And the way it was done was by turning this rather poor representation of what's in an image through a long sequence of calculations into a decision of what's in that image. More specifically, what you see here is a deep neural network. A deep neural network consists of neurons. These circles you see on the slide are neurons, artificial neurons, inspired by biological neurons, inspired by the human brain. But obviously, we don't know how the human brain works, so it's very, very loosely inspired by the human brain. And each of those neurons does something very simple, takes in some inputs and then generates an output. But together, if you have a large network, they can do something very complex. And what they do depends on how these neurons are wired up. You see all these edges there connecting the neurons? That wiring affects the decision that neural network is going to make. And in fact, the strengths of the connections between these neurons determine the decision this neural network is going to make. As I change the strength of the connections between these neurons, I can make it decide cab, or car, or dog, or nothing. It's all determined by the strengths of the connections between the neurons. Okay, so now we've reduced, in some sense, computer vision to tweaking the strength of the connections between neurons to try to figure out what's in that image. But that's an impossible task, because in practice there'll be millions of these connections to tweak. So how do we find the right setting? Well, the big breakthrough in 2012 by Jeff Hinton and his then students Alex Zhevsky and Ilya Sutskever was that it turns out by collecting enough examples, example images of cars in this case, example images of cats, example images of dogs, you can have the neural network learn from those examples. You feed in an example. Initially, the neural network doesn't know what to do. What's it going to say? I don't know. It's random initially. It might say cat. But then after it says cat and makes that mistake, a backward calculation happens in the network that will change the weights between the neurons. And it'll nudge it towards now understanding that this is a dog. You repeat this image after image after image. And at some point, something magical happens. This neural network starts understanding when there's a cat in an image, when there's a dog in an image, when there's a car in an image. You might say, well, how well does this work? There's a standard benchmark called ImageNet. There's a competition around it. In 2010, the best entry in the competition had 30% error rate. So it was wrong 30% of the time about trying to predict what's in an image. 2011, not much better. This was traditional computer vision. And this wasn't really going anywhere, it seems. But rather than using traditional computer vision, Jeff Hinton's group came in with deep neural networks. They halved the error rate in 2012. From there, people came up with variations on that neural network, improved performance very rapidly year over year. And in fact, by now, this competition has been retired because human-level error rates have been achieved. So this gives you some notion of why all of a sudden robots might be able to see. But robots need to do more than perceive. They need to act. How to make them make the right decision? Well, a very famous example you might have heard of, big breakthrough in 2015. DeepMind showed it's possible to have a computer beat the human world champion at the game of Go. This was a big surprise. Why? People thought it was going to take decades before that can happen, but all of a sudden it happened. How was it done? DeepMind wrote a program that had a neural network play Go against itself. Talk about the 2017 incarnation here to keep it slightly simpler, but it was just playing against itself. And after repeatedly playing against itself, it became better, 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 and ultimately was able to be the best player in the world. So it's very interesting. It's learning to solve this game by playing against itself. Repeated trial and error, and over time becoming better. In fact, same thing was done for other games. Here are some video games, Atari games. It was shown that a neural network can learn to play from its own trial and error, become better, better over time. So this is very different from the image recognition I talked about. In image recognition, you have an image, and you say this is a dog, and now it has to output dog. In these games or in Go, you're not telling the network what to do at each step. It just knows at the end whether it won or lost. And then it has to do some reasoning about, well, this time I won, this time I lost, that other time I also won. What is common in the games where I won and what's common in the games where I lost? And so tease that apart and from there improve itself. That's effectively what's happening under the hood. It has to try new things it's never tried before to see if that might be a better way to solve the problem. This process is called reinforcement learning, or RL, and deep reinforcement learning is when you apply this process when under the hood there's a neural network absorbing the experience. This doesn't just work for games. You can do this for robotic control. So at Berkeley we investigated this and looked at, can we have a robot learn to run from its own trial and error? So what do we expect to happen here? Well, this robot is controlled by a neural network. And initially, that neural network will make arbitrary decisions because we don't know how to set the strengths of the connections between the neurons to make it run. It's too many connections. Nobody knows how to do that by hand. So what's going to happen? The neural network will take in the current situation, do processing, and then generate actions, torques at each of the motors in this robot. And that'll repeat. It'll control that robot, but actually it doesn't know how to control it. So what'll happen? It'll fall over. But then it'll randomly control it in different ways and different attempts, and it'll start saying, oh, wait a minute. This one time I fell over just a little bit later. I must have done something better. It'll do an update of the weights based on that. And this repeats over and over and over time it gets better and better and better. So let's watch this in action here. Deep reinforcement learning in action. Yes, it's falling over initially, but it's falling over later and later and later. And then ultimately here, what we see is starting to run. And the beauty is that the program we wrote for this can be reused and have a four-legged robot learn to run, can be reused to have a robot learn to get up. No new programming required. It's the same program, a deep reinforcement learning program, and you give it a different task or even a video game, it'll learn to solve that new task. In fact, we gave these simulated robots a very wide range of skills. And not just simulated robots. We can do this with real robots. What you see here is Brett, the Berkeley robot for the elimination of tedious tasks. This robot is going to learn to put the block into the matching opening. You have to learn a vision system and a control system. Let's watch it in action. Initially, it doesn't know what to do, but sometimes it gets a bit closer, and then it'll reinforce that and do better the next time. Keep improving, keep improving, keep improving, ultimately resulting in reliably putting the block into the matching opening. All learned on its own from trial and error. And again, that's the beauty here. That same program could be used for learning another task. And in fact, the then postdoc, Sergey Levin, who led this project in my lab at Berkeley, then went to Google and did reinforcement learning for having robots learn to pick up objects. And one of the beauties, of course, with robots is if you have a fleet of robots, they can all learn together. They can all share the data. And so the more robots you have, actually the easier the problem becomes because they share the learning and you can learn much more quickly than with just a single robot. Now, here's another example, something you might have seen. This is showcasing in-hand manipulation. So this robot hand is reorienting the cube to match the target shown on the bottom right. It's learned this through reinforcement learning. And in fact, this specific result has since been generalized to also solving Rubik's cubes. So that was all pretty cool. But that was all in simulation or in a lab environment. Natural question is, how about the real physical world? How do we get in there? What's the difference? Let me give you a couple seconds to think about that. What would be the big difference between the two? Well, let's step through this. What is that gap that we see between research and the real world? In research, it's a lot about 0 to 1. Try to do something that's never been done before. Never seen, a robot get up automatically, learning to get up automatically, learning to run. Never seen a Rubik's Cube solved, things like that by a robot hand. If there are benchmarks, very often once about 70% is achieved, people move on to the next benchmark, harder benchmark. But in the real world, even 90% is not enough. You need to go beyond 90%. Let me tell a little bit more about that and why that is. So the real world has just a different kind of reliability requirement. Let's consider a typical station in a factory or a warehouse. Maybe you want to put a robot. Okay, so maybe that station has 500 to 2,000 task completions per hour. That's pretty typical. Then now imagine you have a robot with 90% success rate. What does that mean? If it's a slow station at 90% success rate, you still have 50 failures per hour that's going to need fixing up. At a fast station, at 2,000 per hour, you have 200 failures that need fixing up. And typically fixing up a failure actually takes more time than doing the task yourself. So most likely, when you put a robot there and you ask it to do something and it only has 90% success rate, you cause more work than you save with that robot. In fact, realistically, real value gets created if you can bring it down to 1 or 2 human interventions per hour, because at that point, human can oversee multiple robots, intervene as needed, multiple places during that hour, and the robots are really effective. So at 500 per hour, max 2 interventions, we need 99.6% success rate. At 2,000 per hour, max 2 interventions per hour, we need 99.9% success rate. This is in a completely different zone than research tends to operate in. So we need to solve fundamentally different problems to bring AI robotics into the real world than what is typically being done in research. So you might say, if you heard a lot about deep learning in the last few years, you might say, well, okay, fine, we need to go beyond 90%. Who cares? That's easy. We just get a bigger neural network, larger network, more data, and we should get the job done like that. Well, for a very dedicated task like handwritten digit recognition or recognizing cats versus dogs, the kind of task you often see in research, that might indeed be the case, because you have a very narrow task and you can get more and more data to cover the task space. But in the real world AI robotics settings that we want to attack, there's a lot more subtleties in going beyond 90%. Why? You cannot ignore the long tail of real world scenarios. It's just too fat, too many things in that tail. You cannot ignore that the real world is always changing. You can't just train and be done. You need to be able to keep adapting over time. And you cannot ignore it's important to know when you don't know. So let's double click on these for a moment. Real world, high variability, long tail. Research. People work on ImageNet, 1,000 categories, 1,000 example images for each category. Yeah, maybe you can collect more data for each category and do better. Sure. Real world, millions of SKUs. They might be transparent. They might have weird reflections. There's all kind of configurations they can show up in. It can be very cluttery scenes. It's not just isolated objects and so forth. Occlusions. So it's very, very different. And in fact, significant AI R&D is needed to meet real-world demands, to provide solutions there. The real world is always changing. Let's go back to this decision-making of this humanoid robot learning to run. I was thrilled when we got this result. It's amazing to see this robot learn to do things. But look at it. It's in a flat world. It's always the same. There's no real change in its environment. Compare that to the real world. You receive shipments. You got to open the box. You're going to see what's in there. It's called decanning. You unload things from it into your warehouse. Well, people don't stick to any instructions. They just pack it in there and you get what you get. You got to adapt to what's there. It's not a uniform thing you can train against. So again, significant AI R&D is needed to meet these kind of real world demands. And then finally, in the real world, you need to know when you don't know. Imagine look at something like this as a picking room, like, well, how exactly, what am I looking at here? Well, if it's not clear, then you could say, hey, I cannot handle this one. Rather than making a mistake that might take a long time for somebody to come and fix up, I should then decide, hey, this one I'm passing on. Let's give this one to, somebody who knows what to do with it. I'm not going to do it as a robot. So going back to the original question that I started this presentation with, which is, can we bring AI robotics into the real world? How feasible is it? And where will we see it first? Zooming out beyond what we do with our hands, looking at drones, driving, and then hands, Where do we think it's more feasible? What do you think? Drones? Driving? Manipulation? Well, if you think about it from a human perspective, drones seems very hard because we don't know how to fly. How are we going to fly? And now this robot can fly, so that must be really hard. But actually, it's the opposite. Even though we as humans don't know how to, flap wings and fly, drones operate in empty space. Their job is to be in empty space. They're always in air, empty space. So whatever they do is essentially always the same. It's navigating empty space to then go, to some destination. Sure, there are some challenging situations if there's a lot of things moving around the drone, if it's a complicated, tight environment to navigate in. But if I think about something like package delivery, that's just open space largely. And so it's probably more a matter of dealing with regulation and reliability of the hardware than it is about smarter AI robotics to be able to get a robot to go from point A to point B in free airspace. How about driving versus manipulation? Well, in some sense, driving is easier because in driving, you don't interact with objects. You're supposed to avoid them, just like with drones. In manipulation, you're supposed to interact, go in, touch things. So there's an extra dimension of complexity. But then on the flip side, in driving, the cost of mistakes is very, very high. Worst case mistake in driving can kill people. Worst case mistake in a robot picking an item to ship off to somebody is that they get the wrong item or get no item. Sure, it's important to get the right item to everyone, but the cost of mistakes is much more bounded in a robot doing order picking or something similar than it is in driving. So in my mind, even though there's been a lot of focus worldwide on driving, in my mind, the entry point of AI robotics into our worlds is not driving, even though that's where a lot of effort and media has paid a lot of attention in the last 10 years. In my mind, the entry point is robotic manipulation. We need robots that can see, adapt to get to the next generation of robotic manipulation, and we can start building those today because, yes, you need high reliability, but it's okay to periodically make a mistake because the cost is bounded, no human lives at stake. That's exactly why 3 years ago we started Covariant with focus on the manipulation space. So Covariant team pioneered the next generation AI robotics at Berkeley and at OpenAI as public research. And since then, last 3 years, we've privately, in-house, taken this R&D to a whole other level. We've built capabilities that are not, at least publicly available anywhere in terms of AI robotics skills. You might have seen some of our progress in the news. The video I showed you at the very beginning was actually covered in the New York Times and many others. The New York Times sent their reporter to the warehouse to measure that day, exactly what's going on. How reliable is this robot? Is this really, doing the job? And they got it confirmed, and it was a big breakthrough for the first time to see, be able to observe a robot all day, reliably doing AI operations to succeed at that task. Now, what are some takeaways? Zooming back out, lots of AI research progress has happened, but when we look at research, it's largely about going from never having done this thing to having it done once or a couple times. Benchmarks are usually moved on from after achieving 70%. The physical world is hard, unforgiving. Even 90% isn't good enough. Why is that? Why is it fundamentally so hard to go beyond 90% in the real world? There's high variability, so many different things you can encounter in that long tail. The real world is always changing. It's not some static data set. And you need systems that can know when they don't know, have a fallback in place for those scenarios. So, how about the arrival of AI robotics? We talked about this in the very beginning, and I asked you the question at the time, how do you think it'll arrive? When will it arrive? And I'm curious what you think about it now, compared to what you thought about at the very beginning. As I mentioned, then now reviewing our summary here, 2020, in my mind, is the year AI robotics started being real. You might not have seen it because it's actually starting in warehouses. And most of us don't spend much time in warehouses, if ever spend time in warehouses. But the reason I believe it has started, even though many of us haven't actually gone out to see it, is because these are the kind of robots that use AI, modern AI, to see and adapt, which is very, very different from the traditional robotic automation robots you would see in a car factory. This is just a starting point, but it's a big milestone because the level of generalization needed to operate reliably in such a situation is very difficult to achieve. And now that this has been achieved, it'll be natural to expand out from here because these robots are continuously learning as they're operating. So where do I see this go next? Where do you think it'll go next? Well, what else happens in warehouses? Truck loading, unloading, decanting, packing, package sorting, returns processing. Returns processing probably quite a bit harder than the other four here, but all of these are the kind of things that happen in warehouses, the kind of things where repeated motion automation stands no chance. Yet at the same time, with the many breakthroughs that have happened in AI over the last 5 to 10 years, we are now in a position to start making this happen, to start bringing robots in to do these kind of tasks. And again, it's starting with order picking, expanding out from there is how I see AI robotics bring itself into our worlds, make operations more reliable, especially in situations like the one we're in right now, worldwide pandemic. We need our supply chains to be super reliable, don't want to put people at risk. And so we need robots to help out and reliably operate many parts of our supply chain. Thank you. If you have more questions about this, feel free to send me email. Always happy to chat more and always curious to find out what you care about in AI robotics or what you might want to see automated, what your thoughts are on how maybe, AI robotics could play a role in our world and help us out. Thank you.